As can be expected, no belt can last forever. Sooner or later, belts should be renewed to avoid breakdowns. The procedure for belt replacement is relatively simple, and the job can be broken down into the following steps. First, isolation of equipment. Second, removal of old belts. Third, inspection of pulleys. Fourth, selection of new belts. Fifth, installation of new belts. Sixth, tensioning and alignment of new belts. Step 1, isolation, was covered in the first program of this series. This important step must never be overlooked. For purposes of demonstration only, we shall be using a simulated belt drive without a guard. In the workplace, you would next remove the guard in order to gain access to the belts. Step 2, the removal of belts. Begin by first marking the position of the movable unit for later reference. Slacken off the movable unit, which in this case is a pedestal bearing arrangement, but it could also be the drive motor. Ensure that the adjuster screws are wound back and slide the movable unit to slacken the belts fully. Then remove the belts. There should be no need to use levers ever when removing or replacing belts. Step 3. Inspect the pulleys for damage or wear. Physical damage, such as chipping or cracks, could result in serious mishap or injury. Such a pulley should be replaced with a new unit. Check each of the pulley's grooves for excessive wear. This is not always obvious, but by inserting a profile gauge into the groove, you will be able to see if the grooves are worn. Typical wear would appear something like this, caused by prolonged use or contamination with dirt or dust. Ensure that the pulleys are clean and free of grease or oil, which would otherwise impregnate the new belts, causing slippage and deterioration of the belt material. Step 4. The selection of new belts can now commence. It is important when fitting belts to multiple drive pulleys that the belts are correctly matched in respect to their nominal lengths. Let's discuss this a little further. Belts intended for multiple drive use will show a coding, which is a number printed next to the belt label. In this case, the number is 50. 50 is the international standard code for a belt which has an actual length equal to the nominal length. Ideally, all belts on a multiple drive would bear the same codes. However, owing to manufacturing variations, belts may differ slightly in their actual lengths. Every 2 mm variation from nominal length is represented by 1 unit above or below the number 50. For example, a code of 51 on a 1600 SPA belt indicates that the actual pitch length is 1602 millimeters. From a practical point of view, you must ensure that the maximum variation of belt lengths does not exceed that recommended by the manufacturers. The allowable variations increase according to various belt lengths, and for this reason, we suggest that you refer to the manufacturer's chart for the variations. The next step in selection is to know or find out what length of belt is needed to go around the pulleys. There are basically 3 ways to do this, namely, find out from the equipment manufacturer's specifications, use the label information of a removed belt, if it is readable, or calculate the length using a standard formula. Let us consider the most accurate method, namely the formula method for calculating required belt length. To begin, Set the movable unit back to the marks you made before loosening. Next, you must take 3 measurements. First, the distance between shaft centers, which we'll call dimension C. Next, measure the diameter of the largest pulley, which is dimension large D. Then measure the diameter of the small pulley, calling this dimension small d. Now we can apply the formula, which looks complicated but is actually easy to work out using a pocket calculator. We'll do an example in stages. On our simulator, the C dimension is 615 millimeters. The large pulley diameter, large D, is 240 millimeters, and the small pulley, or small d, is 185 millimeters. Transpose these figures into the formula and calculate the result to arrive at a figure of 1898,48, which will be the required nominal length in millimeters. Now look at the belt reference chart under the SPB column and look for the manufacturer's length that most closely matches your calculated length, which in this case is 1900 millimeters. We now order or obtain matched belts bearing the label size SPB 16N by 1900. Having selected the belts required, you can now move on to step 5 and install them. First, make sure that the adjustment has been fully backed off. Correctly selected belts should slip easily across the pulleys, and unnecessary force should not be required. Fit each belt into its relevant pulley groove, and we're ready to begin. Step 6. Adjustment mainly involves obtaining the necessary tension, and on our simulator, this is achieved with adjusting screws, suitably packed to provide enough movement. Equal turns of the adjusting screws and then rotation of the pulleys will ensure correct bedding of the belts as the tension increases. Ideally, a belt is correctly tensioned when the deflection, checked at midpoint between pulleys, falls between the specified amount. Continue tightening and rotating until moderate tension of the belts can be assessed when pressing down on the belts at mid-span. Avoid using your hands upon the pulleys whilst turning them. Rather, use a convenient shaft or other safe means to rotate when necessary. Nip the movable unit's hold-down bolts, and then using a belt tension indicator, proceed to measure the tension. Let's take a closer look at how this is achieved. A belt is depressed at a point midway between shaft centers, and the force F required to deflect the belt by 16 millimeters for every meter between shaft centers is measured. This is then checked against the belt manufacturer's tensioning chart. On our simulator, the shaft centers are 0,615 meters. Therefore, the deflection required is 16 times 0,615, which calculates to 9,84, or more conveniently, 10 millimeters. Referring now to the chart, we consult the tensioning section for an SPB belt to find the force necessary to deflect our belts by the calculated 10 millimeters. Note that 2 force figures are provided. The upper figures listed are for a small pulley diameter of between 140 and 224 millimeters. The lower figures are for a small pulley diameter between 236 and 315 millimeters. As our small pulley diameter is 185 millimeters, we use the upper figures. In this situation, we read that a force of 35 to 50 newtons, or 3,5 to 5,1 kilograms of force is to be applied. The tension gauge can next be prepared, but let's first take a closer look at the gauge itself. You will observe that it has two scales on the barrel. The lower section scale is graduated in millimeters. The upper section scale is graduated in kilograms of force. Two rubber rings are provided to act as markers. These rings can be set by slipping them along the scale area of the barrel. Set the lower marker ring so that its top edge aligns to the calculated or required deflection on the scale, which in our case is 10 millimeters. Next, place the upper marker ring against the edge of the tube or plunger, and we're ready to check the tension. Apply force at right angles to the center of the top belt span. Keep forcing on the plunger until the bottom marker ring aligns by eye to the top edge of the adjacent belt. Remove the tensioner and note the position of the top marker. Note the scale reading at the top edge of the kilogram marker. This indicates the force that you applied. Compare your reading with the chart as we discussed earlier. Readjust the tension, if necessary, until the kilogram reading on the gauge shows the maximum figure specified. During initial operation, or running in, belts may lose tension slightly. However, providing that the tension does not fall below the lower limit specified, there is no need to readjust. It should be well noted that correct belt tensioning is vital to the drive operation. Incorrect tensioning is the prime cause of premature belt failure. When adjusting a single belt drive, use a straight edge across the top of the pulleys in order to provide a reference edge for the bottom marker. It is wise to complete a belt replacement and tensioning task by checking the alignment of pulleys. A suitable straight edge is employed, whereby we can check such conditions as an offset pulley or setback, or non-parallel shafts. The straight edge should be used to check across both pulleys in two positions, one below the shaft centers, the other above the shaft centers. Ideally, the pulley edges should contact the edge of the straight edge when checked above and below the shaft centers. Correct any misalignment by adjusting the movable assembly. Always recheck belt tension after making any alignment correction. Let's take a break now as you get in a little practice with the replacement and tensioning of belts.